that we've structured the marks, it's good no matter what. Okay, so last week we talked about finite difference method. Any quick questions about finite difference before we're ready to move on? Okay, so the idea with finite difference was you discretize your space. So COMSOL is not finite different, it's finite element, which is a little bit different, but honestly, it's kind of related to finite difference. The way that finite difference worked was you let's say you're in 1D, you're implicitly mapping out some kind of shape of your field, right? Temperature versus X. Okay, and what you're doing is you're saying, okay, at this point, I have some kind of finite difference. So you want to solve heat transport, say. Okay, so this needs two gradients. You need this gradient and you need this gradient, right? How do you get those gradients? You go here, you apply your finite difference formulae, and you get, okay, this is delta t, you have delta t over here. You do all your delta t's, and then generally you would also do some kind of divergence of that, right? And the way that you would roll that divergence in is kind of just depends on the, it depends on how you're applying your finite difference. If k, by the way, if k is also dependent on t, technically you need to do finite difference on this guy. This is your quantity that you're doing the difference on, right? Not just your temperature, because that's also the dependence in there. Yeah. Finite element, by contrast, I'm going to jump forward a little bit, says you have something like this. I'm going to fit a shape element to different intervals, something that might look like that. Based on those points, something like a quadratic, you can imagine a line is super easy, right? And then you're going to do the analysis on that. It goes on and on and on. We'll talk about that next week. The way finite volume works is instead of focusing on the derivatives here and getting the derivatives through finite difference, it's going to focus on the divergence of a something. Okay, what this is doing, it's going to jump into control volumes. So if you remember like control volumes from like thermodynamics, mechanics, all that fun stuff, that's what kind of finite volume is really leveraged for. It is, yeah. Sometimes you would call it control volume integral approach, because it's focusing on the integral of the quantity inside a control volume. So in this case, because you're just in 1D, your control volume is just an integral, right? Yeah, finite difference just focuses on writing the derivatives. What we're gonna, yeah. Why you would want to do this is, if you guys remember in computational multiphysics, we talked a lot about fluxes, right? And your flux was in general everything in here. And then you do your divergence, which is in minus out. And that's your balance equation, right? Rate of change is equal to in minus out. Honestly, that's simple, plus your heat transfer. Plus your heat source, your source, okay? When you have advection, in particular, you would have something like this, grad T, let's see, T, okay? Which, if you cascade it out, grad T plus or minus, depending on things, and then you could do something like this. We talked about advection a little bit in computational multiphysics. It's a bit weird and a bit hard to wrap your head around the math, because one wave flowing one way is the opposite of the gradient going the other way. But once you get all that, the whole idea is that your diffusion plus advection can be grouped together into the divergence of a single flux. But now your flux includes your diffusive flux and your advective flux. When you try and do this in practice, what you're going to get is something like, let's see, spilling something into a river, right? That's kind of like the classic fluid dynamics model, right? So the idea is that you have some kind of river. If the river is still, the stream is still, you have water that looks like that. You drop in some cup of coffee, right? And it just kind of spreads out like that, right? That spreading out is smoothing things, right? You start off with a big spike. Come on in. And then you spread it out and it becomes smoother and smoother and smoother. When your stream or your river is moving, what you would have is this guy moving along with your current, and it doesn't spread out right away. It's going to have a very sharp interface. It's going to be kind of localized until it has a chance to mix and kind of diffuse away and smooth out like that. But that, while it's moving like this and propagating like that, without the smoothing, that's your convection, right? That's the transport along with your advection. And that's very hard to model numerically because it has very sharp interfaces, right? Your concentration is like that, and it's sharp down. When you're doing diffusion, sorry, I'll draw this bigger. You draw it in, it goes something like that. When you're doing diffusion, everything is fine. It actually follows the Gaussian, right? It gets out nice and smooth. But when you're doing advective currents, it just goes like that. This is hard to model because you would need mesh sampling, right, on the scale of this guy in order to resolve this. And if you don't resolve it, if you don't have meshing that tight, what you tend to have is all that crap kind of gets all over the place and just makes a mess of it, to be honest. What that means is that finite volume is very, very good for any kind of advective systems, i.e. all of fluid dynamics. So a lot of your fluid dynamics codes are all going to be using finite volume methods, typically with explicit time steppers, whereas a lot of other things are going to be finite element. Honestly, finite difference is a bit niche at this point. But this is the quintessential convective equation, right? You've got, can you guys see that? It's super small, isn't it? Here we go. Oh, by the way, we have figured out what the problem with the book is. It's being mapped to an older version of the book for some reason. I asked Matteo not to change it at midnight yesterday because that would definitely like break the entire thing today. So hopefully sometime today we'll flip the switch and everything will be back to normal. Okay, so this is the quintessential convective equation. You have some quantity and the rate of change is equal to the velocity or your movement, right? C times some gradient. Okay, which is different from this guy. This guy is the second derivative. This one is only the first derivative. Does that make sense, that difference? Typically, they appear together. You almost always, you have some kind of diffusion, but in a lot of cases, frankly, most cases, you would have something like this. If this term gets too large, it's going to dominate this guy and you're going to have numerical problems. Yeah, moving on. Do you have any questions about this? Does this term make sense? We talked about it a little bit in computational multiphysics. The whole idea is, I don't know if I have my slides. Doesn't matter. Say you have some concentration field or something that looks like that. You're standing on the side of the river, right? And you're watching that concentration, that coffee amount, that spill go by. If your stream is moving like that, and you're just staring at this point in the river, what you're going to see is your concentration increasing just because of the slope of that concentration and the movement of the river. Okay, that's what this guy is talking about. But you can also just move this over. You can take that derivative and you can put it out there, and now it becomes part of your flux. Okay. What we want to do is we want to construct our control volume algorithmically. Typically, bisection is the easiest way to do that. So what you would do with finite difference, you've got a square, you've got your unit square, and you just divide it up and you draw your mesh, right? You've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you're expanding your finite difference around each of these points. So central difference, right? Before, after, gives you your first derivative. In control volume approach, what we're going to do is we're going to imagine our control volumes around there. And we need to create those control volumes algorithmically, which probably means bisection, right? So we've got this edge here, you cut it in half, this edge, cut it in half, you can draw your box. And if you do that through bisection, you've Do you know what the term tiled means? You've tiled the space. It's space filling, right? Because this guy is going to have this square. If you're just drawing squares by bisection, right? You've got that. That's that square. Here's another square, different square, right? But you've covered all of space. And that's important because you're literally covering all of space. You haven't missed anything in there. This doesn't require that all of these edge lengths are equal. And we'll see an example of that. And that's another benefit, right? So especially with fluid dynamics, especially near a wall, if you have no slip, sometimes in COMSOL, it'll automatically suggest mesh refinement where it has like the boundary layers near the wall. What it's going to do there is you have some pipe or something like that, and your mesh is going to be constructed nice and tight and refined near the wall, and then much larger further off. And that's because of typically you would have some kind of no slip condition, right? So your velocity profile would be 0 here, and then kind of up higher as you get into the middle there. Okay. A lot of physics equations will contain this kind of this flux term. J in this case, Q, doesn't really matter. The integral over your control volume, right? The divergence of the flux, the integral of the divergence of your flux is equal to the surface integral of that normal flux. That's Green's theorem. Green's theorem is honestly like it's one of those things that it sounds complicated and then you think about it for half a second and it's honestly super easy, right? Literally all it's saying is after everybody, if everybody in the class starts to move around, right? And we look at the classroom as a whole and we want to see how many students have left the classroom, right? We could integrate over all your individual velocities, all your movements, everything like that, have seen who actually escaped through one door or the other door or the window, right? Or you could just count how many people went through the doors and the window, right? That's what Green's theorem is saying. It's honestly super easy. It's just the mathematical formula of that. Nice thing about that, though, is that it transforms this kind of complicated divergence of a vector field integrated over a volume into a surface integral of the normal flux. Literally, how many people are walking out the door? You have to watch that door, and that window. They are super, super common in physics. Yeah. When advection is present, you can get into these sharp interface problems. Did anybody have problems with COMSOL, like running the fluid dynamics? Like you had to crank down like the nonlinear solvers and stuff. This is one of the reasons. The other reasons is because you have because your advecting quantity is actually your velocity itself, which is super nonlinear. But apart from that, you get all these super sharp gradients. Whenever you have like a vortex or something like that, right? Like you're passing your hand through the swimming pool and like all those vortices are spinning off. Imagine your velocity gradients between one part and another. Like that's what this big struggle is here. Okay. Since finite volume focuses on the integral rather than the derivatives, it's actually a lot more robust, this sort of thing. So, for example, conservation of momentum, right? This is Navier-Stokes. Well, no, this is a very simplified version of Navier-Stokes, not quite, right? In the conservation of momentum, literally what you're saying is that the rate of change of something is equal to the divergence of it leaving, to be frank, right? So the number of students times their velocity, right? The divergence of that is the rate of change of students in the room. In this case, your conserved quantity is your mass density. Yeah, blah, blah, blah. Conservation of momentum is a little bit more complicated and frankly looks pretty ugly because of the vector quantity. because it is the velocity itself which is moving in the velocity field. It comes out to look something like this. And again, you have this idea of the change in momentum, mass times velocity, and this divergence of this momentum transport equation. Okay, I won't go too far into that one. And then you have your external forces here. Energy, think heat, frankly, right? So you've got your rate of change of energy, not exactly, there's a whole lot of other steps. I can give you copious papers on that one. The rate of change of energy, right, is equal to the divergence of your heat flux plus your energy times the velocity. That's however it's moving in your moving frame of reference. Okay, blah, blah, blah. This is your work, by the way, thermodynamic work. Electric charge, same idea. Charge density is the divergence of your current. Dilute species is the same thing. Usually you would, have you guys ever written it in this form, in the chemical potential? Usually you would write it to gradient of the concentration. So more generally, it's the gradient of the chemical potential, but everybody just kind of simplifies it down to the concentration. Okay. Yeah. So let's see how it works with the regular grids. This is an example. It's a 3D one, but we can just assume that delta Z is constant everywhere. So of course that's not going to matter, right? We're not going to worry about the front and the back. We have this uneven spacing, and we have two different boundary conditions. Here it's insulated. Here we have convective cooling, and these are different materials. Our grid is roughly regular. We do have H, but here it's subdivided in only one dimension, not the other dimension. Okay, we're going to consider the steady state heat equation. Negative divergence of flux is 0 everywhere, and we're going to say that the flux is lambda thermoconductivity. Yeah, sorry, this didn't format correctly. Grad T, and let's draw our control volume. So we've got something like this. Let's look at probably, well, yeah. I'm going to show you guys the hardest case from which everything else is honestly a lot easier. Consider the temperature at this point, right? Coordinate 4, 2. What we're going to do is we're going to bisect all the edges around it. So we've got that guy, we've got that guy, we've got this guy. That's a bit too close. I'll just leave it like that. We've got that guy. This is our control volume. Like that. Okay. And what we're going to try and do is we're going to quantify and write out our expressions for the flux going, are we going in or out? I just writing up. Okay. So we want that flux. We want that flux. That guy. This guy. That one and that one. Does that make sense? Okay. Taking it step by step. On the left-hand side, whatever the heat flux moving in this direction is, right? What we're going to do is we're going to multiply that by the amount of area that we have. So this is going to be, sorry, I should have drawn that equal spacing. This entire thing is H. This is H by 2, right? And we've got our flux times the area, H by 2. That should be delta Z. It looks like an equal sign. Delta Z is just the thickness. Is that better? Okay. So that's this guy. On the other side, same idea. Whatever the flux is here, H over 2, delta Z. The lower half going up is going to be this guy, right? Times the same factors. And then we need another one for this side over here, right? So we're breaking up that area piece by piece. We're multiplying through by those fluxes, and then we're adding them all up. The flux up here is 0. We don't have to worry about it because we know that this is insulated up here. So we don't need to worry about that guy. And then we have some kind of convection equation, whatever our boundary condition over there, times the area over there. All right, so good? Okay. Now comes the magic. I'm trying to get this all on one plot here. Okay. The heat flux over here, what we're going to say is it's approximately whatever the temperature difference is between these guys over the space, which is H, times our thermal conductivity, Ka, right? That's going to be our J left. J right, similar on the other side, except now we have a different spacing, right? Since this from here to here is only H over 2, whatever that temperature difference is, divided by 2, and that's your heat flux, right? You do it for the lower one between 4.2 and 3.2. So these guys, right? The difference there is H. Basically the same thing on the other side too, but now you have a different material. So that's your thermoconductivity in A, that's your thermoconductivity in B, and your convection is whatever it is typically. So in that case, this is, okay, that's bad nomenclature. H is not your step sign, H is your generalized convective loss, right? And it's typically just whatever the temperature is there. Difference between that and some ambient temperature, you're just generalizing it. And then you smash it all together, right? You've got all the parts of your equation. You plug all these guys into this. You get this big nasty thing. And now you have an algebraic equation for all of these guys. Which one? Which J? Yeah. Since J is negative K grad T, we're not doing like normal finite difference with grad T. All we're doing is we're just doing, well, yeah, we're doing the equivalent of forward difference or backward difference, to be honest. So this is just going to be minus K T final minus T initial over your step size, which is H, right? So here it's literally just the 4.2 node minus the 3.2 node divided by the space between them. So it's a super simple approximation for that that gradient. Yeah, exactly. Yeah, yeah. I think generally speaking with finite volume, they want to keep the irregular mesh, which means that they can't reliably use higher order derivatives, right? Because it is first order, right? Like what we learned last week is that this guy is only order H accurate, right? We had other ways to make that more accurate, but that required the regular mesh. So for this guy, it is possible in some dimensions, but not all the dimensions. This guy, this spacing is going to be a lot different than the spacing over here. You could make like a more complicated one, but I don't think in general you do that. I think you prefer just to keep it irregular. Any other questions on that one? Okay. What do you do with this guy? You chuck it into a linear system. What do you have to do now? So you did it for one of these points. Now you have to do it for this point. right? And this point is going to be the same idea. You've got your control volume around it. This one is going to be a bit simpler, right? You're going to have your in from the bottom to the right and to the top. The top is going to have two components, one for that side, one for that side. You do it for all these guys and you build up your algebraic system. You're going to get a whole bunch of these equations. They're going to have your unknown vector, which is your T quantities, your temperature quantities. And then you just solve that as a linear system. Okay. Benefits to this is that you can handle complex geometries and irregular domains. Since all you're doing, well, for example, that bisection algorithm can pretty much always find like control volumes around whatever mesh, whatever kind of contorted mesh you're doing. It gets a little bit more complicated when you start to do curves, right? So if you're doing something like, let's see. Something like that, right? A lot of the times what people will do is they'll take that curve and they'll just make it into a facet and just ignore it, to be entirely frank. That guy becomes that guy, that guy becomes that guy. And then all you have to do is repeat your calculation exactly like that, right? Those are your temperatures. That's your spacing there. This is going to be a slightly different spacing. This is going to be different from over here, but it doesn't really matter because you can just algorithmically step through that thing and build up your system of equations. One of the big benefits is that it inherently conserves quantities, right? So all of your mass transport, your energy, your momentum, everything like that, it's specifically designed for that. Boundary conditions are applied non-invasively. What that means is that over here, your convective heat loss, right, is only dependent on that temperature, T42, and the T ambient. Even though, so in COMSOL, what we would try and do is say that your heat flux at the surface is equal to, let's say, J T minus T amb, right? Just flip the sign, times H. And this is going to be equal to your thermal conductivity grad T at that point. What that means is that your boundary condition is having an effect on the temperature gradient inside your material, right? To the point where you could actually say, a priori, right? Whatever your convective heat transport is here, whatever your boundary condition is, you can use it to calculate the slope of the temperature at that point, right? It's a little bit invasive from the standpoint of the linear system because it is pushing that gradient information into your system, as opposed to just saying whatever it is equal to this on the boundary, and then letting it internally find whatever gradient it wants to be. Right? Numerical robustness. So there are actually theories that say that this is like a numerically robust way to do it. I think finite element also has numerical, like mathematical robustness behind it in terms of finding solutions. I don't think finite difference does, actually. It's kind of funny. That's like math major graduate studies level. Okay. It can be more complex to implement compared to finite difference, right? Finite difference was super easy, especially on structured grids, because it's literally just the difference equations, right? You can actually just write out those difference equations as equations, chuck them into a root finder, and off you go, and you're done with it. It can be computationally expensive because you can get large systems of equations, which is going to be a problem in a lot of cases, but we do at least have our linear solvers behind us. You might have to have fine meshes. especially where things are changing, because you're only focused on that integral over the entire thing. If you have something like this, right? If this is your boundary layer down here, and you are concerned about the integral of everything over here, whatever is happening in this direction, in the vertical direction, is going to have a much larger effect on your system than whatever flux is happening along the boundaries, just because of the size. Just because you have that much spacing that you're integrating over implicitly compared to that thickness there. Okay. Yeah. This is one of the noted drawbacks to finite volume, that you can include numerical diffusion, which is the smearing out of sharp gradients that are physically present, but then through your algorithm, this thing kind of like smooths out. I'm hemming and hawing about that one because honestly, that's every algorithm is going to do that, and that's just an accuracy thing. But okay, it is a fallacy of this particular algorithm and all the other algorithms. And it still requires careful consideration for stability criteria such as the CFL condition. What the heck is a CFL condition? I'm glad you asked. Any questions about finite volume? Because this control volume only goes half the step size. Because then you don't get tiling. In order to get tiling, so this control volume belongs to this node. This node also has a control volume. And if you're doing it by section, if you're doing it through bisection, then this control volume looks like that. Does that make sense? Correct. Yeah. It has to cover up the point in the way that the entire space is filled. So I think I do see what you mean. Hold on a second. So in this particular case, it's because you're on the boundary. Yeah. Something like that, right? So this is your boundary. That's insulation. That's convection over there, right? This guy, you're going to do one of these, right? For this guy, the equations that belong to this is the entire thing. So this is h over 2 from here to here. This guy all the way down here is h. This guy, though, is only 3 over 4h. Because you get h over 2 from here, and what is it, h over 4 from here. And then this guy again is h here. Right? So what you have to do through bisection, you can kind of tile this. You can fill it up spatially, but now you get all these weirdo fractions. Right? And then imagine that on top of this, you can still be regular, but now you're skewed a little bit. So it's like expanded in one direction. Like you can, and the software does that, but it does get a little bit messy to build it in. Question? That was it? Yeah, okay. Let's see. Any other questions? I wasn't expecting to get through it so quickly, actually. Another one? Yeah, okay. Just trying to think of a good way to say it. In finite difference, what you would do, we talk about Lagrange multipliers in finite element method. We talked about optimization. We talked about equality constrained optimization. Did we talk about Lagrange multipliers for boundary conditions at all? Weak conditions, weak boundaries. Yeah. Okay. Okay. say you're in one dimension, temperature X, and you know over here your heat flux J out is equal to 10, right? And you have your thermal conductivity K is equal to 1, right? Just make it easy. When you're doing it through finite difference, you're going to discretize your space. What you're going to say is you're going to have to use forward difference over here, or our nifty little trick with central difference, which kind of amounts to the same. So let's just go with forward difference. What you're going to say is T0, T1, T2, T3. This guy, the forward difference, T1 minus T0 over H, right? 1 for the K is equal to 10, right? And then what you would do here, you would do your second order central difference, and you would build out the rest of it. So that would be what? T0 minus, what is it, minus 2? T1 plus T2, I want to say like H squared, something like that, whatever. Central difference, central difference, central difference, okay? In putting in this boundary condition, you have put on a constraint. You've added an equation onto this relationship between T1 and T0. So you forced that gradient to be 10. Okay? With finite volume, you don't actually do that. What you say is whatever the heat flux is through this boundary. Sorry, no. You say that the heat flux is equal to this, right? T ambient, so minus 10. Let's say 10 over there. You just put that in as the heat flux itself. You haven't directly imposed anything about the temperature. Need a bigger screen. You haven't directly imposed anything about the temperature between these 2 points. Yeah. So what that means is that the finite volume equations are going to be consistent with this heat flux through that side, the convective heat loss, as opposed to finite difference, which is, well, the gradient there is equal to it. Does that make sense? It's kind of, it's a weird way to think about it. It's gonna find the same solution. Here's the magic part. It's gonna find the same solution because like the solution to your equation doesn't depend if you're using finite difference, finite element, finite volume. It can't. Absolutely can't. So at the end of the day, your heat flux is going to look something like that. Your solution is going to look something like that, right? In one case, though, you are forcing this slope as a constraint into your equation and saying right away, this slope is going to be equal to this. That's your finite difference approach, right? And most of your finite element method. With finite volume, you say, no, no, no. You know that the heat flux here is 10, and finite volume method can do whatever it needs to do in order to make that happen. You don't directly tell it that. And it gives it that little bit of extra flexibility that makes the algorithm a little bit more robust. The solution has to be the same. Absolutely has to be the same. Any other questions? Okay. Starting tomorrow, not tomorrow, Thursday, we're going to jump into PDEs. PDEs are kind of funny because that's the one that, frankly, we're actually going to be doing a lot of. It's going to merge what we talked about with the boundary value problems and the initial value problems. if you remember the whole stiffness issues that we encountered with forward time stepping, they're going to come back and haunt us. And it turns out that it actually depends on your step sizes. It's called the CFL condition, and it is the bane of our existence, to be entirely frank. What we're going to find, though, is that a lot of our analysis for implicit versus explicit time steppers are going to carry over almost directly. So a lot of the times with CFD codes, first of all, CFD is going to really favor finite volume because it has that implicit conservation built into it. Really favors that, but it's also just going to do explicit time stepping. And all that means is that you need to take really short time steps, but you're still kind of robust, right? So then if you imagine like, any kind of fluid dynamics, any kind of vortices in the swimming pool, whatever, right? Like you're constantly spinning off all these little things. Turbulence, right? Turbulence is kind of a nightmare. It is actually super short time scale, and it is actually super sharp gradients. So if both of those things are happening like that, right, like you may as well just use a method that efficiently takes super short time steps. Okay. I've got another one. Okay, finish that thought. As opposed to things that are a lot more smooth and diffuse, and fortunately for us, that's actually like a lot of what we're going to find outside of the realm of fluid dynamics. So heat transport, mass transport, elastic fields, electric fields, quantum, right? Doesn't like sharp gradients, right? There's like the natural prohibition against anything sharp happening out there, right? There is one other interesting application for explicit time steps that I do want to quickly point out, and then I'll let you guys go a little bit early. If you have any ideas for the projects and stuff, now is a great time to talk about them. I don't know what they're called. The simulations, and actually, if anybody's really keen on this, I would also accept a design project on this one. It's called LS Dyna. It is the simulations of like crash testing, right? So I showed. There was a guy that I met in graduate studies, Brian Leach at Chalk River, and he showed a picture of an airplane crashing into, this is shortly after 9/11, showed a picture of an airplane crashing into the containment structure around a nuclear plant. And he just made it super simple, and the airplane just actually flew into it. So that's why I'm laughing. If you've ever seen those simulations where you have like a car, that was a completely random sidetrack. Have you ever seen those simulations of like a car smashing into something and all the bits flying around? Right? That is predominantly explicit time stepping with something very simple, not even finite volume. In that case, it's basically Monte Carlo. You're basically playing pool. Any kind of like computer simulations of like video games, right? Like destructible environments, you're blowing stuff up, goes all over the place, right? That's also explicit time steppers because in a lot of those cases, you actually don't care if you've got the answer a little bit wrong, right? Like if you want in an example of a crash test, you don't really care if the 500th shard of glass is flying in that direction at that speed with rotating like that, or it's a little bit off. You can tolerate that error because what you really need is, is everybody dead or not? With video games, it's even less like that because all you want is the special effect of everything going like that. So, I do like to harp on the value of implicit time steppers, but honestly, like every tool has a job, and every job needs the right tool. Okay, that's all I got. Come talk about projects. You can look that up. Don't make friends with salad. Okay. Next up is finally partial differential equations. Any questions on projects or nanonuclear? All right. PDEs. Finally, we're bringing together what we talked about with boundary value problems and initial value problems. So PDEs, the general idea is that we're going to have to establish some kind of time marching scheme. What that means is that at every time step, right, we're going to have basically a boundary value problem. And then we're going to be stepping through that in time. And because we're only moving one directionally in time, that amounts to an initial value problem. Of course, whenever we're talking about initial value problems at this point, you should be thinking about stiffness, right? Stiffness, numerical instability, and it comes out to be a big, big problem with this too. We're going to talk about it and quantify it and see what methods we have available to us. Yeah. Time coordinate, is almost always posed as an initial value problem. And and numerical stability is the issue there. Some of you guys might be realizing at this point that time is an illusion, right? And that space and time to a computer are basically equivalent, right? And all it is a coordinate transformation. There are methods, I don't remember what they're called, that do exactly that for various reasons. The difference is that you almost always have your time boundary, right? The big difference between those coordinates is that you almost always have your initial value problem for time, right? You have one boundary condition for your time coordinate, which is your initial value. Sometimes you'll have something on the other side, right? So for example, if you start off with, this is way more advanced, by the way. This would never be on an exam, at least not in this class. Okay, so if you started off with something like, I don't know, concentration, you've got a little bit of dye here. This is your x coordinate, right? And you're saying over here is what? 0. You're fixing that. You're fixing this guy, right? Normally, you look at something like this. You say, this is my initial value. These are my boundary conditions, right? Boundary value problem, initial value off in space. And what you're going to see is something that looks like that, right? You could stare at this thing long enough and just realize that at the end of time, it is going to be flat and 0 across it. And that will be true. So you can, through hook and crook, imagine that you do have actually a boundary value problem in time, too. The question is there, when is this flat enough? And you don't always know that a priori. So in certain circumstances, that is useful. Where's the other one? I think for any kind of oscillation or excitations. So I think a lot of chemical, like quantum chemical calculations, will assume that you have some activation of a core shell structure that returns to its core shape, right, to its ground state after a certain period of time. And depending on what happens in between, those are your boundary conditions in time. And then you can do, I think it's called the method of lines, actually. Anyway, that's a bit more advanced, but just to put that out there that these things exist. Okay. When we talk about time in space-time, there's a big question about how information propagates from your initial condition through to your end. Have you guys heard of elliptic, parabolic, hyperbolic equations? Did they actually mean anything to any of you guys? Right? Me neither, to be entirely honest. And they aren't going to at the end of today either, by the way. The terms are corresponding to something called the characteristics of the equations. That's all I can tell you because I don't understand anything else about it. But there are specific names, and we have to be aware of them. Okay. Equations like this, I apologize. Apparently, we're still having issues with the, maybe it's fixed actually, and just need to reload. We're still having issues with the books. It's still pulling from an older one, and I'm a little bit reluctant to try reloading anything just in case it's broken in the meantime. All right. Equations of this form, where you have some constant, right? You've got your spatial derivatives is equal to 0. They are your elliptic equations. Okay, they are also boundary value problems, right? Because all you've got is your spatial derivatives. You have your boundary condition. You're off to the races. You do not have time dependence here, which implies that whatever is happening so fast that you're not seeing it happen. So for an example, elasticity is my go-to example with this one, right? Have you guys seen The Matrix? The Matrix still a thing. You know when the helicopter like smashes into the building and you see the waves propagating, right? All that's computer generated, right? But in actuality, if you did look at something at a fine enough scale, like my cup, and you saw me pushing it like this, right? All you're seeing on the large scale is this thing moving along like that. But if you look close enough, you would be able to see waves, super small, super fast waves moving at the speed of sound. That's what the speed of sound is. All over this cup, resulting in a net force moving it in one direction. The problem is that those waves are happening so fast, right? Speed of sound, what is it, 300 meters per second over the scale of 15 centimeters? Super fast to the point of not really being relevant, right? That's why we can do this quasi-statically. And this is elasticity in a nutshell, right? We don't have to worry about those waves because they're happening so fast. This is also a trick for how you get around the stiffness problem, right? So stiffness, good morning. Stiffness generally happens. No, one of the things that contributes to stiffness is different time scales in your physics, right? So we had one equation where we had a high frequency oscillation and then the general kind of the slow one too. And what we found out is that we always have to be careful of that high frequency one. Even after it's damped out, even if it's stopped doing that, we still need to pay attention to it, because if not, then it's going to reactivate and it's just going to shake our problem apart. That was in the, I think that was in the initial value problem before we talked about the implicit solvers. You might think the same thing about like the speed of sound, right? Turns out that we don't have to worry about that because we no longer are considering that physics at all. When we look at elasticity like this does not implicitly have the waves in here. That physics, that type of physics is not included in this particular equation. Therefore, we don't have to worry about it, right? That's the magic. Same thing with other stiffness, right? If you go into these big, massive engineering codes, Moose Bison, big one in nuclear engineering, what they've done is they've identified the key ones that cause you problems, and you just remove them. You only insert them when you need them, and then you ignore them otherwise, and now you can get like much larger scaling of these codes because you don't have to worry about the troublesome components. Okay, that was a bit of a tangent here. Interesting thing about elliptic equations is that the information is being propagated infinitely fast. I say not being propagated, it's being propagated infinitely fast. All that you're left with is your final state. It doesn't mean that you aren't changing with time. It just means that everywhere in your system knows about that propagation and everything else is damped and come to equilibrium on a faster time scale. Why this is important, and this is going to be another research project proposal. If you were doing something like banging a drum, for example, right? It's a one-dimensional drum. You've discretized your space. Something like that, right? And now what you have to do is you have to you give this part an impulse, right, at t0. And what you're going to have to find is if you're looking at the hold on, I'm trying to think of how to say this. Say you're just pushing this down like this. So you're doing a static equation. You just want to find like how much your drum surface, your bridge, your beam, whatever has actually deflected. If you are putting this onto something like a supercomputer that just chunks this problem up, and computer 1 deals with this part, computer 2 deals with this part, this part, this part, this part. These are your different computers that are dealing with this, right? Whatever you calculate for here, that information has to be propagated. So those computers now have to talk to each other. This guy has to talk to this guy. This guy has to talk to this guy, to this guy, to this guy. All the way over here, here's a boundary condition. Now it needs to go all the way back, right? You do this, and then eventually you get some kind of nice smooth curve. If you were putting this on a single computer, right, all the memory is shared, the best way to do this is just to solve your equation simultaneously, right? Because you have this information, you write out your linear system, you solve your equation, everything is happy. As soon as you have a cluster, as soon as you have that separation between computers, you're putting this on high performance computing, right? That information needs to be propagated. This is super inefficient for this. If ever you're doing anything like elasticity on a multi-core system, on high-performance system, this is going to tank your productivity. It'll be faster to do it on a single core and just wait to allocate all the memory than honestly doing it on something like 20 different computers at once, just because of that overhead associated with putting all that stuff together. The answer to that, by the way, is something called multi-grid modeling. And if anybody is still looking for a independent research project, take a look at multi-grid. Yeah, multi-grid methods, which are really cool, and they are actually probably the best solvers out there right now. But they were specifically designed for this. All right, let's see. Back to reality. Some of the equations that you're going to encounter that are elliptic are going to be Laplace's equation, Poisson's equation, electrostatics, right? Current generally flows a lot faster for electrostatics than you're interested in. So that's going to be something like that. Heat transport, when you have something quasi-static, you're not worried about the time. Fluid flow, when you don't have like time dependence in there. Problem with fluid flow is that it tends to be pretty unstable. If you're in like a nice simple laminar one, you don't have a problem. But if you're doing one of these things when you're spinning off vortices, that's going to be problems whenever you try and solve those. Okay. Helmholtz equation technically is elliptic because it doesn't have the time dependence in here. That being said, Helmholtz equation is usually used to describe waves. The magic there is separation of variables. And I'm actually going to finish it there. I'm not going to talk about that one more. Do you guys remember this one? Okay, I'm not going to go for that one. If you're looking at Helmholtz equation and you're thinking waves, just think about doing separation of variables. If you're curious, look it up, but it's too far. We'd be doing somebody's talking in the background here. We'd be going down eigenvalue problems and stuff like that. So exercise for the student. Okay. Elliptic problems like this guy, because your information is being propagated infinitely fast, right, require solving some kind of simultaneous system of equations. Typically, they're nonlinear because most things in reality are, which means, how are we solving nonlinear equations? I'm going to wait for the answer here. I'm telling you guys right now. We have a nonlinear equation or a system of nonlinear equations. How are we going to solve it? Root finder, it's written right here, right? What you're going to get is some kind of function, right? Typically your residual, whatever you want to say, as a function of, right? This is your discretization. x0, x1, x2, right? And what you want to know is when this guy is equal to 0. How does that work? You just put in all of your stuff. I don't know. X squared, X, add all of these variables. You're doing finite difference. So now this is X minus 1, X0, X1, 2 over H squared, blah, 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 blah. You have this massive system. You have nonlinearities. You plug everything in and you just chuck it in a root finder and off you go. Easy. After that first step. Problem with root finders. What do you need for a root finder? Written right there. A good initial guess, right? Especially for nonlinear equations. How many roots does a nonlinear equation have? It depends. Anywhere between no roots and infinite roots, right? You have no clue. So, will your root finder actually find the answer? Does an answer exist? No, right? Not necessarily. All it's going to find is its best guess, right? And for that, you need to give it an initial guess. The nice thing about doing time stepping with this sort of thing, so we're actually just like the answer is going to be root finder for all of this stuff because that's why we're covering root finders before we do all this stuff. We're going to be using root finders again and again and again. Whenever you're doing time stepping, what's your initial guess going to be? What's your guess going to be for your root finder? Going for this pie slice here. Somebody tell me what your initial guess is going to be. 0? Not quite. 0 is a great initial guess for linear iterative solvers. But for a nonlinear solver, right, Newton's method, you want to give it some kind of idea of where it should be. Somebody else? And go for the third row at the back. 3 girls with their laptops open. I'm going to give you the answer. If I have my temperature profile at 0, 1, 2, and 3, what's my initial guess going to be for T4? I'm hearing whispering. 3, right? That's a great way to do it. You just take your previous time and you say, this is my initial guess for my next time. Another way to do it is to do a predictor corrector. You say you have 1, 2, and 3. You draw, what would that be, a quadratic through that, right? And you use that to extrapolate out to your next one. Depending on your physics, that can be useful, right? But generally, you would want to use your previous time steps to get an initial value for your next one. Thank you, Outlook, for reminding me that the lecture started 27 minutes ago. Very useful. Honestly, Microsoft, you make enough money, you have AI through the wazoo. How can you not have like Outlook realize that this is 27 minutes over? Like, that's not helpful at all. Question? Me personally, or you moving forward in your career? Finite element is honestly the way to go nowadays. For most things, hit like COMSOL, just because of the flexibility that's inherent in it. If you guys are going to get into something like the nuclear field and you're going to look at the codes, a lot of this stuff is going to be finite difference because it's just too easy. It's too easy to do. Nonlinearity is a snap, right? All you do is you write your derivatives in terms of the variables on either side. You chuck that into a root finder and you will reliably get an answer. Finite element, the entirety of next week is me going to be like doing a show and tell of how finite element works. It's not going to be on an assignment because it's too involved. Yeah, there are classes on the finite element method, and that's all they cover in the entire thing. But that being said, it is super flexible. Yeah, but they also use a root finder, right? So, okay, that's a good one. So I want to hammer this one home. What we're going to be talking about with partial differential equations, we're going to be describing it in terms of finite difference, but it has nothing to do with finite difference, with one exception. Okay, so these properties and the problems, and we're going to get into something called von Neumann stability analysis. That is inherent to the physics itself, not how you're discretizing it. The caveat is that time stepping is essentially finite difference. As soon as you say, I have one time, I have another time, and I'm using those two to calculate the difference, right? Or to calculate the slope, my time derivative, that is finite difference. So a lot of people will still say that's finite difference, even though you're doing like the actual solution using finite volume, finite element, harmonic analysis, anything like that, spectral methods, all that fun stuff. Any other questions? Move on. All right, we cover everything here. Yeah, just a word of warning. Because nonlinear problems can have multiple roots, it is a little bit easy. As you increase your mesh resolution here, what you're actually doing for your system of equations is increasing the space that your solver has to wander in, right? Each of these are basically a coordinate. You have a larger space. It is easy for your system to wander around in that space, Gradient-based methods, Newton-Raphson, again, the go-to, are good for that sort of thing. They're not perfect, in which case you want to do things like global root finding algorithms, line searches, trust region methods. In my experience, to be honest, just take a smaller step size. If you have the previous solution, and almost always you will, with the one caveat being the initial value, because maybe your initial value you don't actually know very well. Maybe your initial value doesn't actually solve physics consistently, right? Which is also unfortunately a problem, and COMSOL has a setting for that. If anybody ever encountered an error that said backward initialization failed, when you're first running it, you probably didn't, but in case you did, that's what it was talking about. Your initial condition wasn't actually physically realistic, and it just had to smooth it out. Yeah, honestly, the smaller your time step, the closer your previous solution is going to be to your new solution, right? Which is going to make that root finding algorithm faster and a bit more robust. Okay, yeah. This whole thing was about this idea of separation onto different computers for high performance computing. This is formally called something called domain decomposition. And basically what you're doing is you're breaking up your domain into puzzle pieces, right? There's this whole algorithm. It's called mesh partitioning. It's not really tessellation. It's mesh partitioning. Whole field of study, how you do that effectively so that you get like different chunks. And then one of the ideas with that is you solve a chunk, you solve a chunk, you solve a chunk, and put it together. And for elliptic equations, that's not a good solution because of that information propagation. However, parabolic equations, that turns out to be a good solution. So with parabolic equations, those are the general differential equations that you think of when I say PDEs. Heat transport, mass transport. What else did I say in here? Anything that is diffusive. Let me run in here. I think the equations came out better like this. Yeah. Here you go. Yeah, it's funny. The exact same formatting comes out differently in like Colab versus the Jupyter book. Anyway. So equations of this form, right? You have one derivative in time, two in space. They are your parabolic equations. What that means is that typically, so this is anything where you have like divergence of a flux, right? Which is actually conservation, which is very common in physics. Typically what's going to be happening is that you're going to smooth out any kind of discontinuities. So if you have diffusion, you start off with a spike, right? What you're going to get is this kind of smoothing behavior, which is very nice. And if you have some kind of like noise generated, right? We're all worried about like error propagation and stuff like that, right? If you have noise and all of a sudden this does one of these guys, right? The next time steps are kind of naturally going to be one of smoothing those out. It is useful. It is not 100%. There are a lot of cases where it's going to fall down. Typically, we regard most physics as being diffusive because they are the conservation equations. First in time, right? Second in space, which is divergence of flux. Technically, that's also breaking causality. This is another advanced topic. The problem is that there's an implicit assumption when you say that the flux is proportional to Q is equal to negative K grad T. The problem is that you're assuming instant response of the flux, so that the phonons for heat transport are instantaneously moving as soon as you have a temperature gradient. That instantaneous part is a problem because that implies infinite propagation of information. Yeah, this is graduate level, past graduate, to be honest, because nobody actually does this in practice. Nonetheless, it is actually real, which is kind of neat. But what this ends up doing is it actually makes this turning into a bit of a show and tell. What you have to do is you actually make your flux time dependent, and it makes your overall equation hyperbolic, which is your wave equation. So that heat, mass, all this other fun stuff propagates as a wave, not as just the diffusion equation. But again, that's a bit beyond. Okay, we're just going to go past this one. Solution schemes for parabolic generally amounts to time marching schemes. So we're going to discretize time, going from one step to another, and we're going to be solving boundary value problems at each time step. You might be tempted to do something called the inverse problem. And the inverse problem, actually, that would probably be another project proposal. If you're curious, look at something called the inverse problem. The idea is if I have a bar of material and I laser heat a little bit, just right here, right? And I'm watching the temperature over here over time. It's called laser flash thermal diffusivity measurement, right? This is a real technique. You're laser heating one part. You're watching how the temperature over here changes. Can you calculate what your thermal diffusivity is? Right? Your material property. Can we use the overall solution in order to back calculate the material properties? Right? It turns out the formal answer is no, disturbingly, right? Because of the dissipative nature of parabolic equations. What on earth does that mean? The smoothing effect, where little jumps get smoothed out. I'll give you an example here. If I had a pulse here, over time, I would get to something that looked like that. Pardon me? Well, it has, yeah. So there is an equilibrium, right? But it also smoothed towards that equilibrium evenly, right? So, right, if I deposited a laser pulse in the middle, right, and at some time later, it would look something like that, right? If I had a different pulse that was a little bit beside it, at some time later, it would have almost the exact same distribution. So if I didn't know where my initial one was, would I ever be able to calculate it? And the answer is no, right? And if you want like the easy analogy to that, just take it a little bit farther. Your final time is going to be flat everywhere, and now you have absolutely no clue, right? This would be the result of a pulse here with infinitely, 100 million thermal conductivity. This could also be the final state of a pulse here with a super slow thermal conductivity, right? And because it's a continuous thing, it has to dissipate that information. That's the nature of the parabolic equations. But that also is a big thorn in the side of any kind of inverse problems. It also, if this looks like entropy to anybody, it is exactly entropy. Okay, entropy is the nature of entropy is this mixing and this diffusion. It is precisely entropy. Can you reverse entropy? No. Right? After you've played pool, can you, for however many turns, can you actually reconstruct what the original pattern of balls in your original triangle was? No. Not with good accuracy. And the longer you play, the less you'll be able to do that. Yes. 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 Correct. You can't step back in time with confidence. It's like it is also exactly analogous to blurring. right? Have you guys ever seen like the CSI TV shows where it's like, somebody took a photo of somebody's reflection in a spoon on a video camera and they're like, sharpen that image, right? Right? Enhance, right? Enhance is complete bullshit. Never worked. It cannot possibly work. You cannot take a blurry photo and make it clearer. Turns out you can with AI. You can, absolutely, but that is complete and utter horseshit. Right? Like it's made up. It's fabricated. You cannot do that, obviously. You cannot blur something and then sharpen it back again. It is exactly the same topic. It is exactly the same idea. And actually, this propagation is Gaussian. It is quite literally a Gaussian blur, and that is how people solve this thing. Okay. Or you can look at hyperbolic equations. Hyperbolic equations have this form. They are the wave equations. And the interesting thing about waves is that you can backward propagate them. Waves move forward in time, and also you could just reverse that and move backwards in times, right? To a certain degree. Depends how much scattering you have, right? Scattering is the problem with waves. Two waves like this, when they interact, they'll just pass straight through each other. So you can imagine separating them out in time. If you have scattering and the actual like kind of dissipation and everything like that, there's that keyword again, dissipation. Once you have dissipation, then you don't have time reversal symmetry. But before you do that, you can actually get this. And there are methods in particular that will exploit that. Okay. Solution schemes. For hyperbolic equations, one go-to way is to do the reduction of order, right? Again, because you have second order in time, you can create a new variable that is your velocity variable and solve for that as two parabolic equations. That's kind of the standard go-to way. Systems with periodic boundary conditions. So you say that whatever is happening on this side is mapped back over here. How would you solve something like that analytically? What do you do when you see parabolic boundary conditions? What kind of methods would you use? Begins with an F. I see it on the tip of people's tongue. Hey? What? Finite difference? Not quite. What do you do when something is periodic? Keyword, periodic. Fourier, yes. As soon as something is periodic, think Fourier. It's almost always the answer, right? Cheating right there. Fourier is a very, very useful way because things can get a whole lot more efficient. You can use the properties of parabolic equations to do the inverse problem. It gets a little bit more weird because you've got this extra time derivative, but as long as you don't have too much scattering, you can look backwards in time, which is kind of nice, right? And the way to imagine that is if you're looking at a pond, right? You drop a rock in a pond, you see the waves coming out, right? Well, if you just walked into the river and just saw the waves all the way out here, you would know pretty quickly where somebody threw the rock in, right? Your brain knows that. The other way to think about that is sound. If everybody closes their eyes, let's do a live example. In numerical methods, let's do a live example, right? Real applied math. Everybody close their eyes. Everybody point where I am. Don't open your eyes. How did you do that? Right? How could you do that? Your ears are separated enough that you can tell which direction I am and backward propagate that information to where I was. If I was in an echoey room, would you be able to do that? No. Right? A little bit. Depends how echoey it was. If I was in like, the most echoey room in the world or something, right? If you were far enough away from me, you wouldn't have a clue where I was because it's scattered, because it's diffused. That's the inverse problem. Your brain is super, super efficient at it. Okay, I'm gonna start into this, and then I'll put a pin in it for tomorrow. Okay. General approach to solving time-dependent PDEs is to transform them into PV. How many times have I said this today already? Okay. We're going to discretize time as an initial value problem into the current and previous solutions. And we're going to assume that we have some kind of information about that. We need that time boundary condition. Okay. Parabolic case. We're going to look at the parabolic case because we can use reduction of order for hyperbolic equations. All we're going to do is we're going to throw this into our finite difference. So getting from here to here, if you don't know how to do this at this point, it will be on your final, it will be on the assignment. Look back at the notes, right, and figure out how to write this thing. Just a little bit of nomenclature. We're going to do the spatial index by a subscript, I, and the time index by a superscript. Okay, so solution at time t is t to the little t, and the next one will be t plus 1. The easiest way to do this is to do explicit Euler time stepping. What does that mean? For the initial value problem, the explicit Euler says that di t by di t is equal to this guy. Final minus initial over your step. And then we're going to plop this into this equation. Okay? Di t by di t, ti, t plus 1. Can you guys see this okay? Okay? So this guy, we're going to plug in here. We're going to get here. Alpha is, it's called the thermal diffusivity, right? The second derivative, central difference, becomes this guy. We're pausing the whole boundary condition issue right now. Collect your terms, and you get something like this. This R, I'm not sure if it actually has a formal name, but it's going to be the linchpin to this argument. All it is, it's a material property, first of all, which is your thermal diffusivity. And then we're going to collect our space steps and our time steps together. Okay, so this R is our alpha, oops, is this. Okay, people will look at, have you guys covered like this sort of thing before, Crank-Nicholson method, anything like that? Okay, I learned it in terms of these stencils. I'm just going to show it to you just for, it's a nifty visualization thing. It's a little bit outdated at this point. The idea with this one is, given at time, you have temperature at 3 spatial points. You're going to use that to calculate the time, the temperature here at your next time step. Okay, so this guy is your t plus 1. That plus isn't coming through the screen. This is your temperature at time t plus 1. These are t current time, I minus 1, I plus 1, and your current one. Okay, so that's the structure of that guy. 2 minutes here. Let's hope this actually runs correctly. Not that. All right. Thinking. Let's see. Oh, and I want to modify that down to 1. All righty. If we do super small time steps, and we're just stepping through in time, this is our initial value. I should fix the scale here. Okay, it starts off at 1, drops down to 0.6543. Okay, well, that's just gobbledygook at that point. Do you guys see how it's just kind of smoothing out? Yeah. Uh-oh, again. Does this look familiar? This isn't a problem with the code. This is a problem with the physics. Depending on your spatial steps, even just doing smaller time steps, you're going to have all this garbage coming up. Look at this, 10 to the 4. Does this remind anybody of anything? Anybody? Class? Anything? Bueller? No? This is numerical stiffness issues. This is the exact same problem as we encountered with the explicit time stepping method, just applied to our PDE. What do we do with stiff problems? Implicit methods. That's what we're going to talk about tomorrow. Okay, guys, let's get started. Assignment 5 should be out now on A2L. Did anybody see it there? Yeah. Okay. So we'll get through this. We'll have some time to go up over the assignment quickly, and then I think we'll probably finish a bit early today, so that's always good. Okay. Partial differential equations. We're putting together our spatial dependence with our time stepping. The approach is pretty easy, to be honest. Once we have a something like heat transport equation, guess what you have on the assignment? Heat transport equation. What you want to do is you want to apply your finite difference formulae to the right-hand side. At least you're going to be doing it on both sides, right? And what you're going to get is that guy, because it's the second derivative. You just plug and chug that. You have your material property alpha here. And then for explicit time stepping, what you're going to do is you're going to do your time derivative as a forward time derivative, right? So you've got T, temperature T plus 1 minus your current over your time step, right? You plug that in here, you get this, and you just arrange all your terms. Meanwhile, you can also put together this constant just for convenience, to be honest, right? Now you have alpha delta T over delta X squared. That's going to turn out to be important. Some people will show this as a stencil, because what you're going to be doing is, did I lose my whiteboard marker? I did, so chalk it is. Do you have one? I'll take it. Appreciate it. Thank you. Okay. So what you're doing with this guy is you're taking, right, this point, you're looking for this guy, and you're using information from these guys on either side. Okay, so you're connecting these and projecting forward onto that. And that forward-looking part is your explicit part. When you actually do this, run anyway, what you get probably looks very familiar, and I need to edit this. This is your initial time step, right? Your initial distribution. And when we take small time steps, it behaves like we would expect, right? So you've got a little pulse, you're doing heat transport, it's fixed with Dirichlet boundaries at the side, 0 and 0. I should stop this rescaling. Haven't managed to do that yet. But all that's going to happen is that heat in the middle is just going to diffuse and dissipate out the side. Stepping forward in time, right, you see that the maximum is just going. So all that's happening is you got something that looks like that, which is going like that, and like that. Okay? If we try and take larger time steps, right, so we're just increasing dt. When we step forward, it works fine and good, and all of a sudden it gets to nonsense. This is 1e7 instead of 0.1. And the larger time step we try and take, the faster that happens. Just by time iterations. Similarly, and disturbingly, If we try and take smaller spatial steps, watch the faceting of the curve, right? While I'm doing that, get smaller and smaller and smaller. The exact same thing happens, right? So smaller spatial steps will cause all this gobbledygook, and larger time steps will do the same. And both are kind of disturbing, right? This should look very familiar. This is exactly the difference between implicit and explicit time stepping. This is stiffness, right? But now whereas before we could kind of attribute this to differences in time scale from different things that are happening in there, now it's a bit more complicated. So the tool that we have to use to do this is called von Neumann stability analysis. And it's one of these tools that's honestly very, very powerful, but is a little bit weird to think about. What you want to do is we're going to look at that solution in Fourier space. And we're going to look at different waves, different frequencies. And we're going to see whether or not those frequencies damp over time or they expand. Right? They either decrease in amplitude or they grow in amplitude. The ones that decrease in amplitude, they're fine. Any kind of noise that looks like this from one time step to another, becomes smooth, no problem. If a frequency that looks like this grows from one time step to another, that's going to be our problem. That's what's going to shake this thing apart. Okay? How versed are you guys in Fourier analysis at this point? So? Yeah. Would this make any sense to you? Okay. So what we've got, yeah. It looks like a nuclear symbol, eh? We've got like the subscript, the superscript on the other side too. The idea is we're going to take one of these temperature solutions. So this is going to be our time at T, right? And what we're going to do is we're going to decompose that into some sum of, how do I write this here? K. So our imaginary number, this is the index. So J here is the imaginary number. I is still our index. So this is imaginary number K sub I delta X. Okay? What we're going to do, why we're doing delta X here, by the way, is because we're shifting that solution. When we do this, we're looking at the next time step over here. We're looking at the next spatial step over here. We're just shifting over that signal a little bit. Okay? What we're doing is we want to know what happens to the next guy. And how it depends on the previous guy. Specifically, we want every wave number, all of our waves, to damp. We want those to decrease, right? Because if they increase, then they're going to shake itself apart. If they decrease, then it's damped and it's not going to be a problem. Okay, and one of the criteria for stability of these algorithms is that these oscillations damp. They don't grow over time. So between one time step and the other one, we want this growth factor to be less than 1. When you put it into your equation, your explicit update equation, all you have to do is just plug and chug. So you've got your temperature at point I, time t plus 1, wave number k is equal to your current time step, which is this guy. And then the one to the left, twice, -2 times the one in the middle, right? And then the one to the side, to the other side. And all you do after that is algebra. So because you've got the these terms up here, you can split those exponentials, you can group them, and you get down to an equation like this. Yeah. From here, you define your G as the ratio between these guys, and you get an expression like that. And what you need to make sure is that G is always less than or equal to 1. Looking at the cosine, depending on your delta x, the minimum, well, the maximum that this could be is going to be 1, right? So because delta x, you can vary delta x whatever you want, but cos is always going to be between 1 and -1. So if cos is 1, this is going to be 0 and G is going to be 1. 1 is fine. 1 means that you're not damping it, but at least you're not growing it, so it's still deemed stable. At least. Not great, but it's still at least stable. It's not going to shake itself apart. On the other side, if your cos delta x is -1, right? Then you've got -1, minus another 1, so -2, and this turns into this guy. Okay? All this means, this is a fancy way to get around to this condition. As long as this guy is less than 1/2, you're going to be fine. As long as your thermal diffusivity, your time step, and your spatial step squared is less than that, then there's no problem. If your time step is too large, it's going to vibrate and it's just going to shake itself apart. If your spatial step is too small, then it's going to do the same thing unless you shrink your time step. So for computational fluid dynamics, where they use explicit Euler stepping, forward Euler stepping, what you get is you have to take very, very small time steps. So it still can be stable. There is a region of stability for these methods, but it requires very small time steps. And if you mesh refine, right, if you have a smaller mesh, then it requires even smaller ones. The good news about explicit is that it's super easy to compute, right? Because all you're doing is you're taking your current solution, projecting out to the next one. That's fine, but that time step restriction destroys you, to be entirely frank. Usually the magnitude between this time step, the acceptable time step for explicit versus implicit, which is obviously the answer because we've talked about this in IVPs before, is like a factor of 1,000, factor of 1,000,000, right? So even though your computation is super efficient, you're going to have to do 1,000 or 1,000,000 more just to achieve convergence, just to make sure that your thing doesn't shake itself apart. Okay. With higher dimensions, right? This is all in 1D, right? When you go into higher dimensions, this gets a little bit more complicated because you've got more terms in your central difference. You've got the ones on the side, above and below, on the other side like that, right? That corresponds to, again, for even spacing, it corresponds to a change in variable in number here, your scale down here, right? This result is valid also for non-even spacing. Like the fact that this is evenly spaced doesn't change the region of stability, it just simplifies the analysis of it. Okay, so even if we're doing finite element, finite volume, it's still going to suffer the same thing. Question about that guy? Von Neumann stability analysis is honestly one of these shockingly powerful tools that you can use for a lot of different things. What was the other one? Do you guys remember that bridge? I think it was in London. Something that they built the bridge and then a bunch of people were walking down it and everybody started to like walk in sync and the entire thing shook apart. Do you guys remember that? You ever hear about this? Fine. Bridge, England, walking in step. The Millennium Bridge? There you go. Hold on. me turn this off, otherwise I'm just going to hear it. Come on.
Opened to much excitement. But Pounds was fully closed, and it wouldn't reopen for another 2 years. So what went wrong?
Do you see that? All of a sudden, everybody is walking in sync, and you can see the entire bridge doing one of these guys.
Well, it's long, but are they walking together?
Blah, blah, blah.
Be one cycle a second, which is the frequency with which their colleagues to walk a step with this, which caused more people to get in step with the bridge, which made more people.
Yeah. So the idea with that one is that when everybody was walking down the bridge, right? When one person starts to sway like that, everybody else compensates by kind of following the same thing. It's the same thing you do on a boat, right? Like when the boat is going like that, you kind of go like that. And if you're not careful, you're just going to flip the boat. So one person started doing it. Everybody fell in sync. And you just kept doing this thing until the entire bridge just kind of shook itself apart, right? That frequency analysis, it's structural frequency analysis, right? That is exactly von Neumann stability analysis. All it's saying is whatever your bridge is, whatever your structure is, if you look at the response from different waves, are those waves going to amplify or are they going to damp? And if they're going to amplify, you're boned, right? Because then it's just going to grow and it's going to crash. There are other ones. Some of the structural ones, like the buildings, things like that. Was it Tacoma Narrows Bridge? I think was another example where that was wind activated because of the way that the railing was or something like that. It hit a resonant frequency, right? Resonance is defined by frequencies that double up and grow and grow and grow and grow, right? It's the same idea. This is kind of the general case for it. Okay, what's the alternative? Obviously implicit. Instead of if you remember for explicit time stepping, what we did was we said t at t plus 1, position I. We projected forward like that, which has the benefit because they have every time step, you know the complete solution from the previous one. Alternately, this looks exactly the same, by the way. We could discretize our time step a backward Euler. And backward Euler is almost the same, right? It's certainly written down the same way. But whereas here we said t at time plus 1 minus t delta t is equal to all this guy at time t. Previous step. We're going to switch that. So this looks the same, but now our right-hand side is evaluated at t plus 1. Okay, just make that one clearer. So explicit would be these two are the same. This is temperature at time t, time t, time t. These are all at the next time step. This is where the stencil kind of comes in handy because you can see it a bit more clearly. Instead of using these guys to project forward, you're finding these guys that match whatever it was at the previous time step, right? Hence the implicit part. You're not finding an explicit solution. You're finding this one that is consistent with the previous one. And the benefit to that one is that whatever your current behavior is, looking backwards is a much safer bet than whatever your previous one looking forward is. Another example that I was thinking on the way here was if you are pushing a trailer, right? Or you're pushing something, a shopping cart, right? If you're pushing it from behind and you've got one of those wobbly wheels, the thing is going to go all over the place, right? Unless you are like super holding it tightly and like not doing anything, right? But if you know, you walk in front, you grab it and you pull it. And now all of a sudden it only goes in a straight line, right? just from moving behind the thing to in front of the thing, you're automatically correcting and damping all those vibrations. Actually, I like that one, right? Because you got that wobbly wheel that's just like throwing up all that junk, right? And you don't want it to grow. All right. If you look at the error analysis, what you're going to find, just like we found with the implicit stiffness IVP problem, it results in a flipping, your reciprocal, in which case your limits of now 1 over g are this, which turns out to always be stable. Backward Euler time stepping is unconditionally stable, which is really nice. Doesn't mean you're going to get the right answer, right? You will necessarily get the wrong answer. And the larger your time step, the more wrong it's going to be. But at least the damn thing is going to converge and you're not just going to end up with noisy stuff. So when we run this guy, I think we were a bit more ambitious with this one. Yeah. So this one, I didn't even show the time stepping. I just showed the entire time series. No matter what your initial condition is, your time step is always going to smoothly decrease. Let's see if we can change. I don't like doing live demos, but let's try and find it anyway. Spatial step size. Let's make it super small and make the number of steps like that. Dun, 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 dun. Oh, I think I just, oh, yeah, that's going to be messy. All right, well, super fine time steps, no problem. You can always find it. If you do, yeah, well, right. Backward Euler, unconditionally stable. But first order, right? Because just like we found with IVPs, backward Euler time stepping is robust. It always works, but it's was it order H or order H squared? It's low order. I think it's order H. Anyway, well, let's find out. Second here. Come on. I can figure out how to get out of full screen mode here. Initial value. Yeah. Okay, so it's order H because it's the first derivative. One other alternative is doing it's not really a multi-step method. What we're going to do is use our central difference formulas. Okay, and the central difference, the adaptation to this case is called the Crank-Nicolson time stepper. It's implicit, but it's second order in both space and time, which is nice. So it's going to give us a better answer. And what we have to do is again, we have to average like the forward and the back. Okay. So what that's going to look like is we have this guy. This guy's still the same because there's nothing else we can do with this, right? We only have 2 time steps. We only have our current one and our next one, right? You can't do a normal central difference in space because that would require another one on the other side. We don't want to have to do that. What we're going to do, though, is average the forward and backward methods. So we take half of this guy, which is our implicit one, plus that guy, which is our explicit side. And what we get after we rearrange everything is something that looks like this, which is bigger, but it turns out to actually be the same sparsity as the previous one, as the backward Euler. The reason for that is because the sparsity is only dependent on this guy from the next time step. you're assumed you already know everything in here, in your vector, right? So we're going to use this guy to construct our matrix. All the information from the previous guy goes in here. Yeah. The benefit to it is that it actually achieves second order accuracy. So that's nice. The stencil is a little bit more complicated. It just looks like an ice cream sandwich. That's what I think of every time I see this thing. Example here. Da, 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 da. So this is the matrix sparsity, doesn't change because the unknowns. Why isn't this working? Ah, because it doesn't want to work at all. Okay, let's try and run all. Oh, even the computer knows it's Friday. All right. Well, that's just broken entirely. It's more accurate. It's second order accuracy. All right. Questions before the summary? How these things work? I don't trust. Other opinions aside, my experience is the Gemini tends to fall on its face for more complicated things. It works okay for the small things, but as soon as it gets to be more sophisticated, it either doubles up everything, changes something like small that you thought it was going to work and then it didn't, or just doesn't get the right solution at all, in my experience. There's a lot of analysis coming out now that's actually kind of saying the same thing. There was a blog article I can share when I get back to my desk that was talking about vibe coding. So, like, have you guys heard of vibe coding? It's a complete aside at this point. So, vibe coding is like you telling the computer what to do, man, and it's like doing its own thing, and you make it a plot. Now it's plotting, and oh, it's so great, right? I think it hit popularity like a year ago or so. All these big companies that are doing, because this like multi-billion dollars, right? The big companies that are looking at this are seeing that it's actually decreasing productivity by about 20%, not increasing it at all. And the problem is that and there was this one guy, a computer science professor or something. I'm on a complete aside at this point, right? There was some computer scientist or some like industry professional or something that that kind of ran these things through. I think it was using Claude, which is like regarded as the best one for this sort of thing. Even though you gave it your nomenclature, you gave it all the passcode, you told it explicitly what to do, it would systematically kind of ignore what it was told and just do its own thing anyway. And even though it got like 80 or 90% of the way there, the amount of time that it took, like, have you ever inherited somebody else's code? Right? And you're just like, wow, this code kind of works, but it's garbage. Like, it doesn't work completely. And it's faster for me to just redesign the entire code than it would be for me to figure out what on earth like Joe Blow actually did. Right? That's what they found on like the Microsoft scale. Right? Like, even though it was getting it like 90% of the way, like instantaneously, going back and correcting all the structure, all the modularization, all the libraries, everything like that was taking more time than it was actually worth. So for the assignments, I mean, I'm true to my word, right? For the assignments, go for it. By all means. Try to focus on the critical thinking side of it rather than the implementation. And that's what I'm hoping that you guys are gaining out of this stuff. When you get out there and you start to do like a master's thesis, design project, co-op, something like that, be careful. It's pretty systematically being shown at this point that it's not good for writing code. apparently there was a talk by Dell Canada chief something. I think AI Factory is Dell's thing. I don't know. He was saying that they did see a 15 to 20% increase in productivity when AI was being used to scrutinize your code. So it would come back and you would write your own code and you would say, hey, does this make sense? Where is the bug? Don't correct the bug. Tell me where the bug is. Is my nomenclature right? Am I calling the libraries right? It seems to be working better as a critic than as a generator. Actually, pop feedback. What's your experience? Are you guys using it more as like a generator or like a critic? Yeah. Very, very useful. Holy hell, useful. Never have to remember plotting commands again. Oh my God. You guys are lucky, man. Python. Python is like, plot this. Okay. Make it red. Okay. Like, try like Java or C. Like plot CR, Fortran. Oh my God. Some of the nuclear codes are written in Fortran. You know what Fortran is? Fortran is character limited. Your variables can only be 6 characters long. Right? And what's worse, your lines can only be like 80 character long. So everything has to be crammed in. And then you have go-to statements. I think that like luckily that thing went out with the dinosaurs. It's like you go through your code and it's like, okay, go to line 20. Different thing. Like object-oriented was just coming out when I came out. Like, right? No. This used to be all procedural by effing line number. Do you have any idea how hard it is to debug a code that can randomly say, go back to line 372? No compartmentalization. Awful, awful. Nuclear legacy codes, man. Ah, but they work. And they work reliably, and our reactors don't melt. So you kind of have to use them. But yeah. Do you guys remember Y2? I guess you wouldn't. Have you guys ever heard of Y2K? Right? Okay. Well, I don't think you guys were alive during it, right? There were people making massive amounts of money because they actually knew Fortran, right? Or assembly. Even where Ethan isn't here, he was doing assembly over the summer, right? Like just going back. So back in the day, Fortran was so memory limited that they only had space for 2-year characters, right? Because they never foresaw that these computers would still be around when it went from like 1982 to the year 2000. So they just tracked 82. And they were like, oh my God, this thing is like going to roll over to the 2000 millennia, and we're going to reset all our dates. We're going to go from 98, 99, 00. Oh my God, all the banking systems are going to, like, all the interest calculations are going to die. Turns out that absolutely nothing happened as far as I'm aware. I don't know if it's like a testament to the thoroughness that they went through this or whatever. Anyway, anybody else, how you're using Gemini? You know what? I'm going to table that one. I'm going to finish this. I'm going to go through the assignment. So there's one more thing that I need to, one more tool that I need to give you guys, then talk about the assignment. And then we can go back and rant about that one. Okay, that's 16 minutes. All right. Implicit time steppers are the thing to do with stiff problems. All of your problems are going to be stiff, right? This is the easiest that it's going to get. This is quintessential like transport. Any kind of diffusion, any kind of heat transport is already throwing this problem. When we did the initial value problems, it was the problem that we looked at was what? Di y by di t is equal to y. Right? Like it doesn't get simpler than this, and they're already stiff. Implicit time steppers. Or you do explicit and you just do a whole bunch of them really fast because they also parallelize. Let's see. When you are doing implicit time stepping, you are going to have to solve for systems of equations at every time step. Even better, right? Paying attention to this one. Since finding the solution to a system of equations, of linear equations, amounts to finding a root of that equation. But root finding, right? If you don't remember why, you've got a something is equal to something, just bring all that to one side, and now you've got a root finder, right? Find the root of this. Nice thing about this is that generalizes to nonlinear cases. Nonlinear in finite difference is super easy. All you do is you plug in wherever you have a derivative, just make sure you're a derivative, make sure you're applying chain law. If ever you have a nonlinear equation, apply your chain law first, right? And then you introduce your finite difference equations. And off you go. You chuck that in a root finder and it'll just find the root. It'll do all the linearization, all that jazz. It'll take care of all that for you. Okay. Explicit time steppers are conditionally stable. It limits the time step in a known way. You can tell a priori what that limited time step, what the maximum time step that you're going to be able to take is. Or also you can just look at your next solution, like heuristically. You can look at your next solution, say, hey, are you doing one of these guys? If yes, kill, go back, try again, right? Like you can imagine an easy algorithm there, right? Nice things about it is that it avoids a root finder. So you don't have a linear system to solve, or at least not one that you're solving implicitly. You can distribute it. You do one chunk, you do one chunk, you do one chunk. All of those chunks are independent. You just shout out your answers at the end and then you move on to the next time step. You can't do that with an implicit time stepper because yours depends on yours, depends on yours. You guys have to be all working on the same sheet of paper at the same time, which is a pain. If your time step is small enough, it always converges, which is nice. When you're doing a nonlinear implicit solve, hopefully you'll converge, right? Maybe you're going to get into other problems. Maybe your initial guess is not good enough and your root finder will never converge, which is a problem. Typically has smaller memory use because you're not storing and building and manipulating matrices. Okay, iterative linear solver routine. The magic is when is the magic point, right? Between an explicit and an implicit. Unfortunately, I don't have a hard and fast answer. In my experience, my personal experience, as soon as you're doing multiphysics, you may as well do an implicit time stepper and just bite the bullet. Your time stepping capability is your range of acceptable time steps is going to vastly outweigh any computational benefit that you have from just doing a simpler one over and over and over again. I can tell you right off the bat that peers in my field do the exact opposite. And they have access to machines with millions of cores, and they just throw this thing on it and they just grind through this sucker. And nobody cares, right? Because you've got the machine, you may as well use it. Fun fact, a lot of the machines that you have for completely other purposes, like code cracking and weapon isotopics and spying on other people. But anyway, the actual valuable stuff. Okay. The last tool that I want to give you guys is something called non-dimensionalization, and I realize that I don't actually have it in the lecture notes. Have you guys ever talked about non-dimensionalization before? I don't think I have it. No, I don't. Am I really not? Okay, well, it's there. Yeah. Okay. Have you guys ever heard of non-dimensionalization before? No. Okay. The idea with non-dimensionalization is in some problems, especially if the professor is being tricky / trying to counter people just throwing it into Gemini. I don't know who would do that. Right? There are cases where you are going to be asked for a general solution. So for example, just randomly, you might be asked to find a solution to something like this. And you will not be given what alpha actually is. What do you do? Somebody said something? Almost, right? What you can do, alpha is just a constant, right? In this case, because you're in a linear system, alpha is just a constant. What you can do is just roll it in and scale one of your variables accordingly. It's called non-dimensionalization. It's a whole field in itself. The idea is that you're eliminating the differences between the time dimension and the space dimension. That's where the term comes from. So what you do is you redefine your time step, for example. And instead of solving for time, you now solve for t prime, which is equal to t times alpha, right? dt prime is just dt times alpha. And your solution, instead of being in time, becomes in dt primed. Excuse me, t primed. The benefit to doing this, so another situation, right, where you might encounter this is in the spatial extent of a problem. So if you were doing something that went from 0 to a, and you weren't given what a was, what you do is roll in that value into x. So x would normally go from 0 to a. Instead, you say that x prime is equal to xa. And now xa goes from, or sorry, x prime goes from 0 to 1. When you plot your solution, what you're actually plotting is your temperature versus x prime, which is xa. I think that has to be divided by, doesn't it? Okay. That scale goes there, chunk through the mouth. The benefit to doing this is that you can get solutions which are independent of the parameters of your problem, which is very, very powerful. You're finding general solutions instead of specific solutions.